Right, topic 11, look at some sections of this now. Uncertainties and errors in measurements and results. This is what we need to take from it. You can have a read through those. Pause me. Now, two terms to get straight from the offset: accuracy and precision. So precision, you can see we've got good clustering, so something like 3 or 4 decimal place balance would have a high level of precision. We'd expect very close together values, but its accuracy may not always be spot on. If it, for example, hadn't been calibrated correctly, someone hadn't zeroed it before they used it, it would be inaccurate. Right? It wouldn't be getting the right answer. So we need to know the difference between these terms, accuracy and precision. We also need to understand the difference between a random and a systematic error. So random errors primarily centered around the uncertainties in equipment, which we'll talk about in a moment. They can be reduced by repeat trials. They can give you answers that are higher or lower than the accepted value. Compare that with systematic, which will always give you a change in your data in the same direction. Right? And they usually arise because of poor experimental design. No matter how many trials you do it, you're always going to have the same problem, so you're always going to have the same error. And an example would be a calorimeter experiment that you've maybe designed where there's heat loss coming out the top of the calorimeter. You're always going to get heat loss. It's always going to change your results in the same direction. So if we're reading something that's got an analog scale on it, that you actually read yourself, then our uncertainty that we quote for that piece of equipment, and we should quote it when we write our equipment lists, whenever we write up tables of data, should be in the header row. It's half of the smallest increment. So if you're reading a thermometer that's marked off in, it should be degrees Celsius, in degrees Celsius intervals, then the smallest increment would be half of that, so 0.5. If it's a digital device, you read it to the smallest decimal place. It's something like some scales that are 2 decimal places. The uncertainty is plus or minus 0.0. It's a stopwatch, it's plus or minus 0.0 seconds. If you're using data loggers, then very often uncertainties will be listed in the manuals that come with them. Something like a stopwatch, maybe when you're writing your evaluation, whilst we can talk about the uncertainty here, then it's more likely though that your reaction time is going to be not that sharp. So something to talk about in your evaluation. And very often, if you can't, for example, a pipette sometimes, or a volumetric flask, sometimes they won't have an obvious uncertainty for you to read. It might well be written somewhere on it. So have a look at it and you can record it from the glassware itself. So as we take down our data, I said that the uncertainties needed to be listed in the header row of our tables. Here's an example of a straightforward titration of hydrochloric acid with sodium hydroxide. So we can see there's our uncertainty of the stuff that we've pipetted out. There's our uncertainty in our burette reading, half of the smallest increment. And it's important we also record qualitative observations. So we could write down about the solutions being colourless, what happens as we reach the end point, and so on. But as well as the quantitative, we must also have qualitative data. So processing the data, you can see my recorded data is, I should have mentioned this on the last slide, it is agreeing with my uncertainty. So I've got the same number of decimal places. And if we look at the stuff that we've got, so all I did was work out the volume of the titer by subtracting these numbers. This is the actual amount that you've added. So this is the amount that you've added, and you can see here that my uncertainty seems slightly different. And it's a fine point, but because I've kind of read this twice, here and here, and then I just did an additional subtraction, then my uncertainty I can just add. Right, so the total uncertainty is now 2 times 0.05, which is 0.1. Right, so this is my data that I've got, and looking at that, that first run seems to be anomalous. So I'm going to ignore that, and I'm going to work with these two. And to work out our titration calculation, this is what's going on. So I can work out the number of moles of HCl that I've got in there. The number of moles is concentration times volume. So my concentration is that. My volume is that. Which means my number of moles is going to be 2 times 10 moles. Put some decimal places in here. Yep. And looking at my ratio, I've got 1 to 1 ratio, so I'm going to expect to see that many moles of NaOH. What's my volume of NaOH? Well, I need to work out my average titer, which is going to be 50.025. So my number of moles is equal to concentration times the volume, which means my concentration is 0.133 molar. Now, looking at this, I've recorded this to 3 significant figures. Right? It's 3 significant figures there, because the smallest number of significant figures I'm dealing with, according to my data, is this. However, a slight problem. It should actually only be to 2 significant figures. The smallest, the smallest number of significant figures used is 2 here. So I can't quote to that. I need to quote my final answer to 0.13 molar. I can say that that's two significant figures, because the smallest number of significant figures that I actually used, I was looking at these and I was wrong. The smallest number of significant figures that I used in my calculation was 2. Right? So there it is. 2 significant figures. Final answer goes to 2 significant figures. Now, as you saw, if we're adding or subtracting data, when we're looking at that second burette reading, I was able to just add the uncertainties. If I'm doing something more complicated, like I was on the last page with some multiplying or dividing, I need to add percentage uncertainties. So if I go back to this slide, and I want to now process my uncertainties, well, the uncertainties I've got are relating to the volume of HCl and the volume of NaOH. I haven't got any uncertainties for the concentration of that. So I need to get some percentage uncertainty so I can quote the overall uncertainty with my final answer. Which means for the HCl, so the uncertainty due to the HCl is going to be 0.1 divided by 20 times 100. So it's the uncertainty over the reading as a percentage, which comes out to be 0.5%. And then for my NaOH, the uncertainties associated to that I've used in my calculation, it's going to be 0.1 divided by 50.025 times 100, and the uncertainty there is 0.67%. So my total uncertainty that I've been working with is going to be 1.17%, and that means I can quote my final answer with its uncertainty, 0.13 molar plus or minus 1.17%. I should convert that to the same unit, so I do 1.17% of 0.13 is going to be 0.13 plus or minus 1.55 times 10 to the minus 3. And quoting our uncertainties to one significant figure is probably fine in terms of a rule of thumb. It certainly has to be less than what we quoted our final answer to. So that would mean it would be plus or minus 2. Alright, so get these, find their percentage uncertainties, because I was doing some multiplication here. I can add them together to work out a total uncertainty, and I can quote that total uncertainty against my final answer, just to one significant figure. That's fine. Another small point, percentage error. So we're able to look up maybe data book values, and we can use them to work out how far away from it we are. Please notice this is different to percentage yield. So if that's our actual value, the value that we worked out is 0.13, which means, using this equation here, we found that it was 0.13. Then the difference between experimental actual value, well that's 0.01, divided by the actual value, which is 0.12, as a percentage is 8.3%. So that's your percentage error. And what you can then do is you can go on to look at, well, that's how far away I am from the answer. How does that line up with my uncertainties? Is it covered? Is the problem down to the equipment? And you can see, well, the limitations of the equipment was only about this big. This is how far away you are, so there's another problem in this, and probably some systematic errors creeping in as well. Right, reminder of the things that you needed to cover. Have a look through those, and you will be sure to be practicing these with many of your experiments that are coming.